How about object that, like in this case, you have the sphere object that moving and the path of rotations. That means if you look after at some point on this cross section of the cylinder, or maybe a bowling ball, this part, when you look after the red dot, this part is changing with the time, and we call this part, whether it's on this side or in on the rims, we call it as a cycloid because it's moving like a semi-cyclic. So it's moving and keeps changing if you have some reference point like this. But if you trace on the center of mass, you can see the center of mass is moving like a straight, not straight, sorry, like a straight line. Although the rims keep rotate like a centroid motions. This is the benefit of knowing the center of mass, because in terms of having rigid body or rigid object for rotation calculation, or you would like to determine how this motion happens, if you have the center of mass as a representation, you can trace the center of mass at the center of this object. And if you have the velocity, you can link the relations between v of the center of mass to r omega as well. How can this happen? This is look similar to our translational quantity as s equal to theta r, v equal to omega r, and a equal to alpha r. However, in this case, what we look after is v that happen in tangential, and a also happen in tangential. But in this case, we said that our v that we look after is from the center of mass translations. How can this happen? Because if you look after the s part here, this is the part at the rims. When it keep rotate, that means you have a distance here equal to s, and this s, you can see, is has the relation similar to the thing that we call the angular rotations. Think about thing that rollings. If you have this position as a mark, and when it's rollings, that means it keep moving for a s distance, which is this distance is also have a linear distance as s. What you have seen the center of mass moving from this point to this point, similar to a point at the rim rotate for s. This is somehow you can link the relation of s, that this center of mass moving equal to and theta, that the spherical or cylinder object rotates. This is a kind of like different definitions from this center of mass thing to the one that we look after at the tangential key of the definitions. But the similarity is when you translate the information of the arc distance like this to a linear translocations, you can see the center of mass moving in the same distance. So that somehow you have s of center of mass that moving equal to r theta. So when you dip this term, dip s by dt, you will have velocity of the center of mass, which is equal to r omega as well. And acceleration of center of mass also r alpha. So the translational is accidentally having the same. But to be realized, you can see in detail is slightly different. But in terms of definitions or how we solve to the system, we can use the translational quantity to explain about things that happen of this object that rolling on the ground. So this rigid body or rigid object can be translated by using the center of mass as a representation. This is what we did state initially. Its object is purely rotate. That means there's no center of mass. This is pure rotation. This object only rotate like a wheel, not moving forward. So you can see this velocity of center of mass is equal to 0 for this case. However, if it's pure translation, at the top and the bottom of the point of this sphere and the center of mass, they both are the three of them, they have the same center of mass velocities. So in this case, it's only translation happens. But if you look after, in this case, this means this object rotate and translate. So this is have both translation and rotation. By this, you can use the definition that we know about, or how to find VCM, ACM, to use the four major kinematics equation to explain how these objects translate or rolling through the times. With that, if you look after the kinetics here, so the kinetics that happen can be both from translation. Sorry for my tongue twisted. And this is the rotation. So you have to take account on both translational kinetics energy and also the rotational kinetics energies. To calculate this is the reasons behind these four different objects rotate and translate with different velocities. Not only due to the moment of inertia, you can link to the way that kinetics energy and of translation and rotation involved into system. And also because initially they have some mgh, which is the potential, we can link all these together and using work and kinetics energy theorem to explain the phenomenon that happen of this rolling motion of a rigid body. So let's look after this example. So from this problem, as you can see, the solid sphere this translate on the slope and also rotate as well. So the both rotational kinetics energy and translational kinetic energy can be applied. But initially, this solid sphere, placed on the top of this slope with the h height from the ground. So imply that if this from the red state, so it contains the potential energy, the gravitational potential energy, mgh initially, and after that is rotate and have the velocity from the center of mass to take account with. So in this case, if you use the conservation of energy from the first event equal to the final event, what happened in initially? So you have mgh as if you count as this point as the height, so from this position it has mgh. But when it's moving, what they have the to this position, this end reach to the ground, so there's no potential energy, but have translational kinetic energy mvcm square, and also the rotational as plus 1 over 2 I omega square. Since you know that omega equal to V over R or VCM, if you look in terms of definition previously that what we state, so we sub VCM over R here. So what you're gonna get mgh, and also this term, like in the both kinetics of the translation and rotation as 1 over 2 mv square cm plus 1 over 2 I v cm square over r square, like this. So if you would like to have the term of this relation in terms of v cm, how can you apply with it? So you can just get v cm outside, and also the term that you have 1 over 2 m here plus 1 over 2 I over r. And this is the form that kind of like similar to, you can reduce this to kinetics energy like 1 over 2 mv square. For example, if you look after v cm like this, you can have kinetics energy of total both rotation and translations in terms of 1 over 2 some things and v cm square. You would like to set to this form. How can I arrange this term? So if I write it carefully, I can rewrite this term become 1 over 2. You have here I cm over r plus m and multiplied v cm square. So this term is like mass that you take account with the moment of inertia and the mass of the objects in terms of the relations. If you would like to determine the velocity, which this term is equal to mgh, you have to take maybe m outside as well. If I would like to take m, that means I multiply m's and m's over here. So I can rewrite it as the term of the factors. So this is 1 and m, I get it outside. So this can be m over r square. So this is r square over here. It's my fault. Right, so that this term is mr square. So now you have these kind of factors that relate to the moment of inertia. If you look after here, ICM and mr square is look similar to the definitions of the moment of inertia from the particle point of view. But look these as the factors. So now you would like to convert to have only the center of mass velocities, and then you can convert to acceleration later. So I'll get rid of big M of it. So you have VCM equal to here this 2GH over 1 plus ICM over MR square. So this is the term that you have. I will write it properly. So I'll remove this part. So I'll write on this area. So now you, after rearrange this term, you will have this as the derived velocity of center of mass that relate to the object that rolling from the height h or from the slope to the ground. So this is equal to 2GH over 1 plus ICM over MR square under the square root, because this is a square. So now you got VCM already. If you would like to determine the acceleration of the center of mass, how can you derive this? Surely you can rearrange this term, since we know that the solid sphere has moment of inertia at the center of mass is equal to 2 over 5 mr square. So now we can sub 2 over 5 mr square here, so that we have finally VCM equal to 10 over 7 GH, and this is under the square root. So I will write a power up with 1 over 2 as square root instead. So now after I sub right down here, sub I equal to 2 over 5 mr square in, and rearrange the term, you got this result. If you would like to determine the accelerations, how can you use this relation to have the accelerations? Okay, you did learn about the kinematic equation on the slope, because now we look after the translation of VCM. So figure out if you have the relation of V square equal to V0 square plus 2AS. In this case, so your V now is VCM, and V0 also 0cm. A now is ACM. And S is the distance that this object translates, which is X distance. So now you can find the relation, since the initial velocity u or v0 is equal to zeros. So this term is zeros. So now you can have the ACM equal to v square over 2s. In this case, it's the x, right? Because this distance is x. So now we put v in so that v equal to 2gh, or I can just write the value that I sub in already, 10 over 7 gh. When square, the square root is gone, over 1 over 2x. This is 5. And finally, you will have this in meter per second square. All right, this term over here is equal to 5 over 7 gh over x. But as you can see, the relation of h over x here, this is h, this is x. This is the definition of sine theta. So you can write this term rather than gh over x is equal to 5 over 7 g sine theta in meter per second square. If you want to define the ACM of this motion,